Okay, welcome to the next lecture. So here we're really going to sort of start our journey on looking at the different types of radio sources that we find in the sky. And we're going to start with a particular type of source called an H2 region. These are some of the strongest radio sources that we see when we look at objects in our own galaxy, the Milky Way. And we will see that they are a very good way of tracing regions of where massive stars, so the stars that are sort of 10 to 100 solar masses, are in the process of being born. Okay, so H2 regions are associated with star formation and the birth of stars. So we'll have a look at their radio properties and derive a few simple expressions and look at their spectral output. Then we will have a brief look at sort of looking at seeing H2 regions in other galaxies before returning to look at some other kind of extended nebula types of galactic radio sources that we see again when we look in our own galaxy. So we'll also be putting into action some of the radiative transfer concepts that you've just been hearing about. Okay, so this is a little busy cartoon showing us how we believe that sort of massive stars evolve. Let's just look at the panel in the middle here, which represents an evolutionary sequence of how we think the formation of massive stars proceeds with time. So all star formation starts with basically sort of what astronomers would call dense, cold molecular gas, interstellar gas. So the space between the stars has gas in it. Some of that is in a sort of cold, dense form where all the gas is in the form of molecules, so that the hydrogen would be molecular hydrogen. And in these regions, if you get enough gas and you get it cold enough in a small volume, then gravity can get to work and it will start to condense and collapse on itself under gravity, and that's indicated in this cold collapsing core schematic here. So that gas starts to fall inwards to the center, and quite quickly in the center you will form what we would call a protostar, which is then held up by pressure in a hydrostatic equilibrium, and the center of the star will start to heat up and get denser and denser, and material will keep falling in on top of it and keep adding away. As you will hear later in the course, that involves sort of accreting material via a disk and bipolar outflows and all sorts of crazy things that go on during star formation. So you'll hear about that later in the course. But once that star really gets hot enough and luminous enough that it's basically starting to put out hard ultraviolet radiation, this is where we get interested because it will start to form a bubble of ionized gas around it, and that is an H2 region. Okay. Over time, that H2 region will expand and break out in various ways, and eventually, these don't form in isolation. You've got a whole cluster of them, so you will end up with a new cluster of bright, young, hot, massive stars. Okay, so it's this end of the sequence that we're interested in this lecture, where we have this ionized gas, and that's because it's the ionized gas that emits strongly in the radio end of the spectrum. So these are spectra of these different stages running along the top here, and at the end, at the long wavelengths, you can see suddenly a tail of strong emission, and this is in the radio end of the spectrum. And so again, you can see it developing here. Okay, so that's what we're going to focus on. So just to recap, an H2 region is a region of ionized gas that surrounds a massive young star that has recently formed out of this collapse of a molecular cloud. And so it's the leftover gas that's in that surrounding molecular cloud that is ionized and forms the H2 region. Okay. I guess I should explain H2 once more. So this is spectroscopic notation for ionized hydrogen. Okay, so H Roman 1 is atomic hydrogen, H Roman numeral 2 is ionized hydrogen. And it's really only the massive stars that are hot enough to ionize hydrogen. Okay, if we go back to the hydrogen energy level diagram again, then the cold hydrogen in these clouds is going to be in the ground state, and so we need to give it 13.6 electron volts of energy at least if we're going to get the electron from the ground state and liberate it from the atom to ionize the gas. So 13.6 electron volts corresponds to a photon with an energy, energy of photons is either h nu or hc over lambda, where h is Planck's constant and c is the speed of light. So that corresponds to a wavelength of just under 100 nanometers. So it's up in the far ultraviolet part of the spectrum, which only hot stars emit. Okay. So just to reinforce that point, let's return to our Hertzsprung-Russell diagram, a plot of luminosity against temperature, going backwards here, for stars. And here we're just plotting what's called the main sequence, which is where stars are born when they are burning hydrogen in their cores. And this is labeled by stellar mass in solar masses on this particular version of the diagram. So to ionize hydrogen, to get a lot of photons with that wavelength of 100 nanometers and shorter, you need at least about 30,000 Kelvin to be the surface temperature, the effective temperature of the star. Again, you can check that just with Wien's displacement law for a black body. The peak output of a 30,000 K black body would be around about 100 nanometers. But we can see on this diagram, okay, if we want to get to 30,000 here on the x-axis, we need to be at a mass of around about 10 solar masses or larger. So it's only these stars at the top end, the massive end of the main sequence, that are going to be that hot when they are born. Okay. As you can see, they're also very luminous. So that is why H2 regions are only associated with the formation of massive stars. Okay, let's now have a little look at the physical conditions in a typical H2 region. They do vary a lot, but these are just typical numbers. Normally, certainly when we're talking about sort of interstellar gas, and we mentioned physical conditions, we're normally talking about the density and the temperature of the gas. That's sort of two fundamental parameters. So the typical number density in an H2 region would be about 10 to the 10 particles per meter cubed. So you will notice here that we're using number density rather than mass density. We're not talking about kilograms per meter cubed. We're talking about number of particles per meter cubed. Okay, and again, that's very typical for interstellar astronomy. We normally talk about the number density. Now, just a little caveat here that unfortunately astronomers are still rather wedded to the old CGS, centimeter gram second set of units rather than the SI units that I know we're all supposed to use. So you would, most textbooks and refereed papers and everything, you would normally see this number density written in per centimeter cubed. So that would correspond to 10 to the 4 particles per centimeter cubed. Okay, remember a centimeter is obviously 100 times smaller than a meter, and if we're talking about a volume, then that's going to be cubed, so that's 10 to the 6 times smaller. What about the temperature? Well, a lot of the photons will have an energy somewhat higher than the 13.6 eV threshold that's needed to ionize the atom of hydrogen, and so that extra energy will go into the kinetic energy of the electron that is liberated. Okay, so if you're putting additional energy into the kinetic energy of the particles, the electrons, then that is going to manifest itself as an increase in temperature. And so the gas is also heated as well as ionized. And a typical temperature for an H2 region, and they're all fairly similar actually, would be about 10,000 Kelvin. Okay. So this is much hotter than your typical atomic gas in interstellar space, which is only about 100 Kelvin. And much hotter still than the molecular gas that it was originally in, the state it was in, which is only about 30 Kelvin. So what's going on inside the H2 region is basically what we would say it's in a state of ionization equilibrium. So this means there's a balance between these two processes of photoionization on the one hand and recombination on the other. So photoionization, and that's expressed in this kind of reaction equation here, is where you take your hard ultraviolet photon with some energy, h nu, nu being frequency again, and that intercepts a hydrogen atom and breaks it apart into a proton and an electron. Okay. So going to the right is the photoionization process. But at the same time, there is recombination going on. So you can see the arrow is going leftwards as well. So an electron will encounter a proton and recombine to form a hydrogen atom again. And in so doing, it will emit some radiation, okay, like a bound-free process. Okay. So it will emit some radiation. And the balance between sort of these processes, basically, you can use that to determine the initial size that the H2 region will have when the ultraviolet photon source of the star turns on. So let's work towards writing down an equation for that initial size. That initial size is referred to as the Stromgren radius, after the German astronomer who first worked this out. And so we're going to, just assume some very simplifying conditions here. Let's assume that our star is in the middle of a constant density medium. Okay, so it's got a constant number density that doesn't change with distance from the star. That is not true in reality, but it makes this easy. So we've got this kind of geometry. So when you've got a constant density and you turn on the star in the middle, it's going to ionize a sphere of gas. So the H2 region will be a sphere with this outer radius Rs, okay, for some given number density n here. So we need to look at both sides of this sort of balance. Let's look at the photoionization part first. So for that, we're going to need to know the number of ionizing photons that come out from the star. So that is characterized by this quantity here, n Lyman continuum. So Lyman continuum is just another word for photons with a wavelength of less than the sort of 100 nanometer-ish threshold for ionizing stars, or for ionizing hydrogen. Okay. So we can write an equation for this. Okay. So let's characterize our star by its luminosity. So luminosity is the power in the radiation coming out from the star. So that will be normally in joules per second, but here we want it as a function of frequency as well. Okay, so it's joules per second per hertz. So if we take, the amount of energy per unit time here and divide by the energy at that particular frequency, we're going to get the number of photons. Okay, and we just need to add them up over all of these frequencies that are higher frequency, higher energy than that threshold, corresponding threshold of 13.6 eV. So that's an equation way of doing it. Graphically, we can look at an example here. So these are different black body curves representing different temperatures of stars and their spectra. So here is where that sort of threshold of just below 100 nanometers is for ionizing hydrogen. And I've just drawn a line on here. What we're interested in is all of the photons that are shortward of this line. So this is a bit of a low temperature here, so there aren't very many. So you can see this hatched area here. So this is the area under the curve for wavelengths shortward of the threshold. Okay. As you can see, as the temperature gets hotter, this peak will move further into the hard ultraviolet and will eventually, a lot of photons will be shortward of this line. Okay, so that was the photoionization side of the equation. Let's look at the recombination side. So to characterize the number of recombinations of protons and electrons per unit volume, then that's just given by this expression here, where alpha h comes from atomic physics, and it basically determines the rate of recombinations. But of course, it's a two-body process, so you've got protons and electrons, and the rate at which they recombine will be higher if you've got more protons or more electrons per unit volume. And so any kind of two-body process depends on the number density of each particle involved. So that's why it ends up like this. So we can now characterize the equilibrium by equating these two processes. So we've got the number of photonizations on the left-hand side. If we assume every single photon that can ionize hydrogen does so somewhere in the H2 region, and balance that with recombinations throughout the H2 region. So this was per unit volume, so we would need to integrate over the entire volume of the nebula. But because we've assumed it's a constant density nebula, then nothing in here depends on distance or anything. So we can just take it outside and multiply by the volume of our sphere, which will be 4/3 pi r cubed. We're going to make another simplification here, that the gas is very close to being totally fully ionized, which means you've got one electron for every proton if it's pure hydrogen, which is a good enough assumption here. And so therefore NP equals Ne, and so we're just going to call that Ne squared. So this will be the electron number density. And so we have a formula here, which relates the number of ionizing photons with the density of the nebula and its size. Okay, and we'll be using this in the workshop later on. Okay, so here's an example again of the sort of most famous H2 region. It's the nearest one to us in our galaxy, the so-called Orion Nebula. So here is the Hubble Space Telescope picture, the optical picture of the nebula. And you can see this thing with your naked eye, actually, in the constellation of Orion. If you know where to look, there's a little misty patch. And this is a radio picture taken by the Very Large Array. And you can see that, they look fairly similar. And, nothing out there is actually uniform density, so it's not a nice sphere, but you can see that it's basically an ionized bubble of gas in space. And the distance from the center here would be this kind of Stromgren radius type of argument that we just put forward. Okay, so we'll have a little break there. So during the break, just take 5 minutes, you can see that you've got the optical picture and the radio picture here. Just have a little look at these and see what's different between the two pictures in terms of the diffuse extended emission. Well, anything really. So what's different about these two images and why would be a little discussion point. Okay, so I'll stop there and we'll be back after 5 minutes.